Hello, my name is Katia Charrière. I'm an engineer at the University Hospital of Grenoble in France, and I'm going to present you ODIASP, clinically contextualized image analysis using the PREDIMED clinical data warehouse toward a better diagnosis of sarcopenia. A project from the University Hospital of Grenoble, the University of Grenoble, and the Clinical Investigation Center of Grenoble. Context. The University Hospital of Grenoble deploys its clinical data warehouse, PREDIMED, to collect data produced during the care of patients into a data lake for the purpose of research in the field of health, improvement of patient care, and steering of the establishment. This video presents a specific PREDIMED use case, the ODIAS project, for which we want to build a clinically contextualized image dataset. The objective of the ODIAS project is to develop and evaluate some tools to automatically estimate the muscle mass of patients in order to better diagnose sarcopenia. Sarcopenia is defined as low muscle mass and/or function and is associated with increased hospitalization time and mortality. Currently, there is no gold standard for the assessment of muscle mass. The computed tomography can be used for sarcopenia diagnosis by computing a skeletal muscle index, SMI, derived from the cross-sectional muscle area, CSMA, at the mid-third lumbar vertebra, L3 level. But calculating this SMI requires some time-consuming manual task. The objective of ODIASP is to automate the calculation of this SMI. The clinical data warehouse PREDIMED will be used to build a dataset of clinically contextualized images, which will allow us to train and evaluate some deep learning-based tool to perform fast and robust automatic CSMA measurements. This will allow us to obtain large cohort of patients with SMI, cross-reference with clinical data for the estimation of new marker of sarcopenia. 2 points will be developed here. The first one is how to fill the data lake with medical images. The second one is how to exploit this data lake to obtain a dataset for the ODIAS project. Methods. The first question is how to copy and incorporate medical images into the data lake. Here, the data lake is a self-distributed storage with 265 terabytes available. A virtualization platform on Ceph hosts several containers. One container is dedicated to image management, while others are dedicated to text management, structured data, and various tools. The architecture used for image management is based on Ortank. Ortank is an open source DICOM server that allows the hosting and exploration of medical images in DICOM format, but also communication with the care production thanks to the DICOM protocol. Our first objective is to not impact the routine care. To achieve this, 2 Ortank containers have been deployed. The first one communicates with the production DICOM server using the DICOM protocol. Network traffic control is set up to limit our impact on the healthcare. The second Ortank container is set up for PREDIMED users with an unlimited traffic access. Both Ortank containers share the same PostgreSQL database deployed on Ceph. An emergency control is also set up to quickly stop our Ortank container and thus stop all communication with the care production. The various tasks deployed for image retrieval from healthcare, and in particular, the orchestration of the retrieval of all new data produced by healthcare, and also a retrospective retrieval of data produced in the past, are orchestrated through Apache Airflow. Finally, the dashboard, based on Prometheus and Grafana, allows us to control our import of medical image data. Next question, how to build the ODIAS dataset from the PREDIMED data lake. The second Ortank container with unlimited traffic access was used to identify patients with abdominopelvian scanner. The administrative data of this patient were easily collected to inform them by mail. Then a set of scanner data was collected after a de-identification step, which consists of removing specific tags and series of images. Associated clinical data required for the study was also collected from the data lake. Results and conclusion. First of all, some statistics. We estimate the medical image data produced by the Hospital of Grenoble since 2015 at 160 terabytes. Currently, 470 imaging exams have been integrated into the data lake, that is about 18 terabytes. About ODIASP, approximately 3,000 patients were quickly informed through simplified mail generation from administrative data from the data lake. Then, a dataset of 676 de-identified scanners with patient age, weight, age, and gender were collected. The images were manually annotated by a clinician who identified the position of L3 vertebra in the scanner and segmented the skeletal muscles in the identified slice. This dataset is currently being used for the development and evaluation of some deep learning-based tool for the automatic computation of SMI. We are on the way of a massive copy of medical image data in the data lake of the clinical data warehouse PREDIMED. The ODIAS project shows a great advantage of clinical data warehouse in clinical research through its ability to generate clinically contextualized image datasets. Some perspectives. For now, we are here. The first dataset has been built for the development and evaluation of a tool for the automatic computation of an SMI from abdo-pelvian scanners. To go further, we are now building a second dataset of 3,000 scanners for which we aim to automatically compute SMI with our deep learning-based tool, with associated diagnosis and biological results collected from the data lake, with the aim to define new markers of sarcopenia. Finally, I would like to thank all the people who contribute to the great ecosystem around the clinical data warehouse PREDIMED and the ODIAS project. Thank you for your attention.